This is an example of a medium level problem on the first order transients game in Circuit Tutor. So we're assuming that the tutorial has already been viewed here, and this is going to be specifically problem type 2 or an RC type of circuit. Okay, so as always, we need to analyze this circuit. It's going to be a transient because this switch is closing at t equal to 0, and that will induce a sudden change in the circuit, which will then behave exponentially as a function of time. So as always, we need to analyze the circuit at several different times. So we're going to begin at t equals 0 minus, just before the switch is thrown, in which case we know that we're going to be in steady state. Then again at 0 plus, we'll need to analyze the circuit. We also need to analyze it at t equals infinity, where we're again going to be in steady state now with the switch closed, and that will give us the particular solution to the differential equation, or in other words, the steady state value of this resistor voltage, which is our sought variable. And we also need to find the Thevenin equivalent resistance viewed from the terminals of the reactive element, that is the capacitor, for t greater than 0, because that determines the time constant, characteristic time constant of this transient. So let's begin, and of course we can always give up if necessary without any penalty, and there's help available. So let's begin at t equals 0 minus. So the circuit labeling has been changed for t equals 0 minus, and we need to reconfigure the circuit and then edit it and analyze it as necessary. So we begin by reconfiguring, and in this special mode of the editor, basically it gives us some instructions here, but basically the only thing we're allowed to do here is to change the switch in the reactive element. We're not intended to simplify in this particular mode of the circuit editor. So at 0 minus, this switch has not yet closed, and so now it's basically an open circuit. So I'm going to select that and change that to an open circuit. In other words, delete it. Press the delete key on the keyboard here, or I could press here or right click if I wished. And then the other thing I need to do is to say, well, here's V0 of 0 minus, but remember that's a resistor voltage. And the thing about resistors is their voltages and currents can generally change instantaneously in time. So what I'm really interested in is the transient for 0 or t greater than 0, and this is actually going to be of no use at all at t greater than 0 because it may have a completely different value. So unless I just want to know what that is, I may as well just even get rid of that sought variable. So I'm just going to bother to throw it away so I don't have to bother finding it. I mean, you can find it if you want to. It just means you have to do a little bit of extra work if you wanted to know that value. So I'm just going to get rid of that sought variable. But what I do need to know is the one thing that cannot change suddenly when the switch is thrown, and that is, as you may remember, the voltage of the capacitor. And that's because I equals C dV dt for a capacitor, and if that voltage were to change instantaneously, dV dt would be infinite, meaning that the current would have to be infinite in the capacitor, and that's not possible. So therefore, the voltage cannot change suddenly. So because of that, what I want to do is to find the voltage at this instant t equals 0 minus, so that I will know what it is at 0 plus when I'm no longer in a steady state situation. And so I'm going to change this basically. Well, before I change it, I'm going to add a sought voltage. Doesn't matter where I put the plus sign. It's pretty much arbitrary. I'll put it on top, I guess. And that's labeled it for me. And now I need to change that because we are in steady state at 0 minus, because that switch has been in the same position for a long time. That means any transients that did exist will have died out. And therefore, in steady state, again, I equals C dV dt. The dV dt has to be 0 in steady state because nothing can change in time by definition in steady state. So that means its current is also 0. And something with 0 current, well, that's an open circuit. So I will change that to an open circuit. Now I don't want to delete it because that would get rid of this sought variable that I very much need. So instead I'm going to change it to terminals, which are allowed to have, in Circuit Tutor, that's allowed to have a sought voltage on it. So basically that's the reconfiguration I need to do. And it's important to keep that in mind anytime you're working a problem like this where you have a resistor voltage or current, for example, that you're trying to find, or anything basically other than the capacitor voltage or an inductor current. So I'm done reconfiguring the circuit. And now I want to observe, can I simplify that circuit? Well, I can probably, these two resistors can be combined in series, so I may as well do that. It's not really going to help very much, but it might help a little bit. So it gives me simplification instructions. So I'm just going to change that 6 plus ohm plus 4 ohm in series. That's going to be 10 ohms. And I'll change this then to a short so that I have the entire resistance here. And I'll check that combination. And then I'll compress the circuit here a little bit just to make it look nicer. And basically that's all I can do at this point, so I will quit there. And as I said, I didn't really have to do that, but I just did it. And now you notice that this is in fact a single loop, because the capacitor is an open circuit, so that doesn't really affect the number of loops. There's really just one loop going around here, two meshes if you will, but I usually call that a single loop. So we'll do single loop analysis, and we want the sought voltage, so maybe we'll start with that. And actually what you may notice is this is really the voltage across this resistor. Now Circuit Tutor won't let you move that sought voltage over here just for technical reasons, although in theory you could if you're doing it on paper. But basically it is just a voltage divider because this voltage is across this resistor, and so really this is just a single loop circuit that's a voltage divider, and so that means I can just use the voltage divider formula. So I'll put in a sought branch voltage, and my VC of 0 minus now is equal to, just using the standard voltage divider formula, I'm going to have the voltage source value, which is 1 volt, and then the resistance across which that voltage appears now is the 10 ohm, because see that's connected directly across the 10 ohm, not across the 2 ohm but across the 10 ohm. So I put the 10 ohm here in the numerator, and then also in the denominator, and then the other resistor will appear in the denominator. So remember that the 1 volt divided by 12 ohms, that's basically the amount of current in amperes that's going to flow here, and by multiplying that times the 10 ohm resistor, I will get, by Ohm's law, the voltage drop across that 10 ohm resistor. Now I do need to always check polarity when I do a voltage divider or current divider, and here the plus side of the voltage source is in fact connected to the plus side of VC of 0 minus, and the negative side to the negative side. So that means that this will be a plus sign. I never want to guess at that because I could make a big error if I get the wrong polarity. So that is correct, and I'll check that. And basically that's all I need, so no more equations to write. I just need to numerically evaluate that. So I just get out my calculator, and that's 10/12 or 5/6 of 1, and that's 0.8333. So we'll check that. And that's correct. So now it's just summarizing what I've done so far, which was to find the capacitor voltage at 0 minus. And it reminds me which way I defined that capacitor voltage, because that's crucial to know, even though it's not shown here right now, because this is just the original circuit drawing. But I do need to have that information, or I wouldn't be able to know what to do with this number, basically. If you don't know the polarity, then you're kind of sunk. Okay, so the next thing we need to do is to go in chronological order and now analyze at 0 plus, which is just an instant after 0 minus. But remember that some things can change as a result of that switch being thrown at exactly t equals 0. Now it tells us that I have to basically reconfigure the circuit and then perhaps simplify the circuit and analyze it. So I'll do that. So the first thing I need to do is to reconfigure the circuit at this appropriate moment of 0 plus. So because I'm at 0 plus now, that means that the switch will have closed. And so now I can change this switch. Instead of an open circuit, it's going to become a short circuit. Now you may notice right away that that shorts out the 6 ohm resistor, which indeed it does, but remember I'm not allowed to simplify just yet, so I'll have to wait a little bit to remove that resistor. Now the other question is, well, what do I do over here? So normally in a steady state situation, you would say, oh, the capacitor is an open circuit because I equals C dV dt, and therefore the current has to be 0. But the point here is that we were actually at 0 plus, not 0 minus. And at 0 plus, remember, we've just basically done something to the circuit. We've closed that switch, and therefore we've initiated a transient. So during a transient, which includes this instant at 0 plus, the circuit is not in steady state at all. In fact, it's having an exponential behavior with time, and we cannot assume that this is an open circuit. So then the question is, well, what in the world do we do with the capacitor? Well, the answer is we have to remember one of the properties of a capacitor, which is that its voltage cannot change instantaneously with time. And again, that follows from that same formula, I equals C dV dt. So if dV dt, that would be actually infinite if the voltage were to change suddenly, and that would give us an infinite current, which of course is impossible. So we're not allowed to do that. And basically what that means is that whatever that voltage was at 0 minus, it's going to have to be the same thing at 0 plus. And it's helpfully put that SOT variable on in the same polarity that we originally defined it. And so the question though is, this has to still be this value, but what does that mean? Well, it means that we have to replace the capacitor now, not by an open circuit or by a short circuit, but instead by a voltage source, an independent voltage source. We can use what's called the replacement theorem. It says if we know the voltage across an element, we may as well call that element a voltage source because it's going to have the same voltage either way, and that won't affect the rest of the circuit. And that'll allow us to analyze things because we know how to treat a voltage source. We don't really know how to treat a capacitor when it's not in steady state. So we're going to take this and change it to a voltage source. And remember that we needed to have that plus sign on the top. That's where this little cheat sheet here comes in very, very handy. So I'm going to change that polarity to match, and then I'll put in that value of the 0.833356 volts. And again, got to make sure that the polarity matches, so that's very crucial, as is always the case in circuits. So now we've changed that capacitor to a voltage source. And again, this is only valid at that one instant in time, but that's when we're analyzing the circuit right now. So now we're done reconfiguring properly, now that we have our source replacing the capacitor. So we're exit the reconfiguration mode. And now, well, clearly we should probably simplify some things here. So let's go into the circuit simplification mode. And now, as I said before, this 6 ohm resistor is shorted, so it would make sense just to get rid of that because it doesn't have any voltage, therefore it cannot have any current either. It really can't have any effect on the rest of the circuit. So we got rid of that. That'll help to simplify the rest of the circuit. And then you might also notice that this resistor is directly across a voltage source. And if you remember back in the third portion of the DC superposition introductory tutorial, we talked about how that means it's redundant with respect to that voltage source, because yes, it's going to draw some current from the voltage source, but I'm not interested in the current from that voltage source right now. If I was, then I would have to keep that resistor there. But since I'm only interested in this voltage, that doesn't really matter. And so this is what we call a redundant element, or it's also called voltage splittable. And so I can just basically delete that. It's not going to affect the part of the circuit that I'm interested in over here. So I can just delete that. And that gives us a little confirmation, an explanation of why that was valid to do. And now I have a single loop circuit, which is easier to analyze. And in fact, we know that 2 voltage sources in series can actually be simplified down into 1 voltage source. And so if we think about the sort of batteries and a flashlight analogy, we see that these are sort of in backwards, aren't they? Because we have the negative going to the negative. So those voltages aren't going to add, they're going to actually subtract. And so here, this is going to be 1 minus 0.8333. In other words, it'll be 1/6 of a volt, or 0.1667. And then I change this one to a short circuit. And then I can check that I've simplified that appropriately. And now, well, this is going to be very simple. So I'm basically done simplifying that. And I can consider that, I guess, as a single node pair circuit if you wish. Doesn't really matter. I can just enter a value for that voltage because I don't need Ohm's law here, because I just want to know the voltage across that resistor, and that's actually fixed by this. In fact, I could have even, well, I guess I couldn't really remove the resistor because it has the SOT voltage, but in any case, it wasn't really playing any role by itself. So the SOT voltage is directly determined by the source itself. And so we just say that that's equal to a particular voltage, and you can put in 0.1667 there. But we want to be, again, always be very careful about polarity, because here you notice that the plus side of the SOT voltage is connected to the negative side of the voltage source, and the negative side to the plus. So we actually need a minus sign there, otherwise that would be incorrect. So again, always pay attention to polarity. Okay, so that is correct, and that's basically all we need to do there. And so now we have the initial value for our SOT quantity at 0 plus, which we're going to need. That's, again, called the particular solution of the differential equation. It's the forced response due to the source in the circuit. Okay, so the next step, I mean, we could do either of these things, it doesn't matter, but let's do t equals infinity first. And once again, I have to go through these same steps, reconfigure the circuit, then simplify and analyze. So let's reconfigure. And once again, this means that I have to change the switch to something more definite. So the switch now is going to be closed because I'm analyzing at t equals infinity, which of course is much greater than 0, obviously. So that will become a short circuit. And once again, this is going to be shorted, but I can't remove that until I go into a different mode in the circuit editor. Now, because I'm at infinity, I don't have the complexity that I had before. Now the capacitor is simply an open circuit because we are going to be in steady state at t equals infinity because now the transient has had time to die out. It takes time for a transient to die out. That's why they call it a transient. So that means that this can be replaced by an open circuit, or I could just actually delete it. I think since there's no SOT voltage across it, I may as well just delete it entirely. So I'll just delete it. And basically that's done now. And then once again, since I have a shorted element, it would make sense to remove that. So I'll just delete the shorted 6 ohm resistor since that plays no role in the rest of the circuit. And now you see I just have a simple voltage divider, so I really don't need to simplify that any further, and there wouldn't be any point. So let's just quit there. Remember, single loop is the objective, or single node pair. Once you get there, don't try to go any farther because you're already at your destination, basically. Those are the simple circuits we try to always have. Okay, so now I'm going to select single loop as the circuit analysis method because, as I said, this is simply a voltage divider. We have a source, and then that voltage by KVL has to drop across each of those resistors partially. So we're going to basically just enter the formula with the voltage divider. So V naught of infinity will be equal to the voltage divider formula, which is the voltage source value of 1 volt. And then the resistor of interest now is that 2 ohm resistor because that's where that voltage appears. And then that'll be divided by the sum of the resistances, which is 2 ohms plus 4 ohms. And again, the 1 volt divided by the 6 ohm there, that's the amount of current flowing through the circuit. Now we have to, again, always pay close attention to polarity. So here we notice that the positive side of the 1 volt source is actually connected to the negative side of the SOT voltage and negative to the positive. So that means they have different polarities. And another way of thinking of that is that the current is going to flow from high voltage through the resistors back to low voltage, because just like water always goes downhill, not uphill. And therefore the current is going to be flowing clockwise, which means we have active sign convention for this resistor rather than passive sign convention. So therefore we must have a negative sign out front. So let's check that. And that is correct. And we're done basically writing equations. So now we just need to numerically evaluate that. So that's 2/6 or 1/3. So negative 1/3 is just negative 0.3333. So we'll check that. And that is correct. And now we have the summary of what we've done. And the only remaining thing is to find the Thevenin equivalent resistance seen from the terminals of the capacitor. So there's always a bunch of steps in these types of problems. So we'll click on that. And once again, we have to reconfigure the circuit, then simplify and solve for the value of our Thevenin. So we reconfigure first. And again, we have to adjust the switch there, and that's going to be, since this is t greater than 0, that switch is going to be closed, so it becomes a short. And to find our Thevenin, remember, we're looking out from the terminals of this capacitor, and so we're going to basically change it into terminals so that we can see the R Thevenin looking outwards from that capacitor. Okay, so again, we do check that there are no dependent sources in this circuit, because if there were, we would have to use a test source to find that resistance. We'd have to use a test voltage source or a test current source, kind of like using a multimeter. But we don't need to do that here, so we will just basically change that to terminals here, and that's automatically labeled for us. And the other thing we're allowed to do here is to kill sources in this mode. But maybe I'll just show you if we don't do it, we can come back into the circuit editor. Oh, and it's also reminding me to remove that sought variable because that's of no interest when I'm finding our Thevenin. So just to make it simpler for the program, we're just going to remove that. Okay, so now we're done. And now we can kill that source. But I said we could have done that previously, but I'm just showing you can also come back in later and do it. And because we want it to have 0 volts, we basically change that to a short circuit. So that's how we would kill sources, just same as we do, for example, in superposition problems. And that's all we do in the source killing mode. Then we could simplify the circuit. I could go into the circuit editor and move this shorted 6 ohm resistor, and then notice that these two are going to be in parallel, right? Because they're connected to the same two nodes. This node is connected to both of them, and then this node here is also connected to both of them. And again, this resistor doesn't even play any role. So I could go in the circuit editor and do all that, but it might be simpler just to say, well, 4 ohms in parallel with 2 ohms, I can compute that directly. So I'm just going to enter that. That's going to be the product over the sum. So 2 times 4 is 8, divided by 6 is 4/3, or 1.333 ohms. And that is correct. And that just saves me some steps there. And now we're ready to, we've got all the information that we needed to find about this circuit. So now we're ready to enter this final transient expression. And remember that on a test, you'll need to know the form of this expression, even though it's kind of giving it to you here. Unless your instructor gives that to you. So here we're looking for a voltage, so we're going to find a transient voltage. Okay, so V naught of t will just be this standard term. And first of all, we have the constant term. Remember, that's the one that's going to survive at t equals to infinity, because at t equals to infinity, we have e to the negative infinity here, which goes to 0, no matter what this constant is. So this is going to be the value of the voltage at infinity. And we computed that as negative 0.333. So we'll just enter that value there, negative 0.3333, not forgetting the minus sign, of course. And then we also know that at t equal to 0, the exponential will just be 1, because e to the 0, of course, is 1. And so this plus this must equal the the V naught of 0 minus, which is the minus 0.1667. So basically, this plus this equals this, so this is going to equal this minus that. So it's going to be 0.1667 minus 0.3333, and that's just negative 0.5. And then the last thing we need, and you can just check that that in fact will add up to this value of minus 0.1667, which it does. So just a third minus a half is going to be minus a sixth, which is this. And finally, the time constant for an RC circuit is always R Thevenin times C, where R Thevenin is the resistance viewed from the terminals of the capacitor. So that's basically 4/3 times 3 farads is going to be 4 seconds. So we'll just put in a 4 there. And then we can check that. Oops, sorry, did that too fast, I guess. So 4/3, well, let's see, let me just 0.333 times 3. Oh, I'm sorry, yeah, that is 4. Okay, so I missed that minus sign. That's what happened. I overlooked that minus sign there because I entered too many digits. So I miscomputed this value. This value is fine. It's this. So what I should have done is taken that minus 0.1667 plus 0.3333. So that should have been 0.1666. So sorry about that error again. I just overlooked that minus sign because it got cut off. Okay, so let's try that again. And that's why they give us more than one chance, I guess. So, okay, so that's all done. And just click no more equations. And we do have the option of viewing the full solution of that, so I'll just show that for completeness here. It does take a moment or two to generate here as it's writing a lot of stuff on the screen. So we'll just have to wait for that. And there's the general strategy that's done. And it's going to do things maybe a little bit differently than the way that I did them. It's doing a mesh analysis here, which is probably not really, to be honest, necessary. That's just sort of its default method that it used. But I think our method was probably even better. And then it analyzed at 0 plus, and again it deleted the shorted element and deleted the voltage splittable element, combined the sources as much as we did, and then of course it simplified the R Thevenin value, and then showed the final value. So basically the same kind of steps we did, a little bit different, but there's, as usual, different options to do the problem. Okay, so that concludes the example at the medium level.